I'm going to be talking about online learning in SNNs with eProp and neuromorphic hardware, as the first slide suggests. First, I'll go over the motivation for this work and the reasons that we wanted to try and tackle these challenges, which kind of leads into how memory works within neural networks, both in non-spiking and spiking counterparts, how eProp fits into that, and how the algorithm developed by Guillaume Bellec in Wolfgang Mass's group was able to tackle some of these problems. Then Spinnaker, which was the neuromorphic platform this algorithm was moved onto, before talking about some of the tasks and then mapping it up. So the first thing is the motivation. So why are we doing this work? So the online learning is a big benefit. This comes from the eProp algorithm that provides a lot of this. So it means that you can have continuity between interacting with an environment and integrating that information that you learn through interaction. So this means that you have no break between acting and learning. Also, when paired with neuromorphic hardware, this means that you can have a local tailoring of the system. So in a robotic scenario, you could have your agent interacting with an environment and updating its system on the fly. It's also the neuromorphic element, which I'm sure you will love, but I'll quickly touch on it anyway. So there's the low power and low latency, or a lot of the benefits from neuromorphic, and that a lot of that comes down to the event-based element. So compared to the non-spiking counterparts, in which synapses have to be queried each time and the multiply accumulates have to be calculated, even if there's no activity at the neuron. When it's with events, it only matters if there's activity being passed through the network. So this takes a lot of inspiration from biology and allows the computing to be more efficient. So the neuromorphic that was used in this case was Spinnaker. So this is a neuromorphic platform which offers real-time computing. So it can, like in the robotic scenario, as mentioned earlier, means that you could have it interacting and learning at the same time. So this is where eProp fits in quite well. And also because of the fact that it's programmable, the digital platform allows you to port these algorithms onto it. There's also the large parallelization of Spinnaker, although the scale isn't touched so much in this work. So the first thing I want to cover is how memory actually works within neural networks. So in non-spiking versions, a common practice is to use LSTMs. So these are recurrent models that allow information to be passed into the network. There's some memory or state that is saved within the LSTM, which allows past states to influence future states. They've shown a lot of benefit in tasks that have temporal elements. So anything like language processing, where you have to combine a number of phonemes to be able to understand a word, or combine a number of words to be able to understand a sentence. LSTMs work well here. And also for video processing. So because you have a number of frames that need to be combined to be able to understand the video as a whole, LSTMs are very beneficial in this scenario. But because they have recurrency, normal backpropagation doesn't work quite as well. So you have to use backpropagation through time, which presents a number of challenges. So because you want to be able to calculate error a number of different time steps backwards in time, this also means you have to pass errors backwards in time as well. So the way this is usually done is that you retain the state through a number of different time steps, and then you enroll the network. So you effectively make the whole network one layer, and then another time step will be another layer, and you would roll those errors backwards, which means that for every time step you want to calculate errors back, you have to do another computation backwards as well. So this is quite computationally expensive, and also not very well suited to neuromorphics. So there's a lot of state that has to be saved. So a spiking counterpart, which is used, is to have adaptive threshold neurons. So this is something that again was used by in TU Gratz and Wolfgang Mass's group, where following a spike from a neuron, the adaptive threshold, or the threshold of the neuron will increase. So every time it spikes, it then requires more input to make it spike again. This will then decay back down with some time constant, but in effect, this allows the neuron to retain some memory of previous activity. So they showed that when applied to the sequential MNIST task, so this is a task in which it's traditional MNIST, but each pixel is presented one after the other. it could perform just as well as LSTMs or its competitive performance. So they termed this the LSMN, so it's the long short-term memory spiking neural network. So there's a number of challenges that are presented from trying to do gradient descent with spiking neurons. The main one is the discontinuity of the activation function. So because when it's below threshold, there's no activity, and when it's above threshold, it produces a spike. This discontinuity means that you can't do differentiation. A technique that is used in EPROP and a number of other algorithms is to use a pseudo derivative. So you make some approximation of what the derivative is around the threshold. So let's now go into EPROP and how it uses these pseudo derivatives. Slightly different formulation to what you saw from the backpropagation through time one, where instead of having to unroll the network backwards through time and retain state of all previous time steps to be able to perform these updates, the only thing that is passed forward is the eligibility. So the eligibility, I'll touch on the next slide, but it captures the behavior of the network. So it's a record of the spikes that have come in, the pseudo derivative, which encapsulates the network's behavior at that time step. And then this is low pass filtered to create an approximation of the synapse's behavior over a long period of time. There is then also the learning signal, which is the error that is produced at that time step is passed along random feedback weights back to the neuron. So these random feedback weights were shown by Timothy Lillicrap to be able to do training with backpropagation. So in backpropagation, you pass the information forwards. You then will pass the gradients back along the same weights, which allow you to associate a neuron's activity with a certain output. But what he showed in this work is that you can broadcast the errors along random weights back to the neurons that have nothing to do with the weights going forwards. And eventually, the forward weights will start to align with these feedback weights. So this is something that EPROP uses to be able to broadcast an error to the whole network. So they're all random. There are individual per neuron and per output. The eligibility is then combined with this learning signal to produce the weights. So as mentioned, they're quite different to backpropagation. So in backpropagation, you have to retain state for each time step. You have to then also do an inference step, and then you have to propagate backwards for each time step that you want to do updates for. EPROP doesn't have to do that, and it's just one forward pass. You retain the state in this eligibility, which allows you to do online learning. And with the adaptive thresholds, you can still also have memory of previous states as well. So it's online, but also can retain memory of what's happened before. So to jump into the math, because we all have equations, the neural model is very similar to leaky integrating fires. You have the membrane voltage decaying. It integrates the spikes from the inputs and the recurrent connections. And then once it crosses threshold and produces a spike, the threshold will reset by subtraction. There is also the adaptive threshold element, which I touched on earlier, where following a spike, the adaptive element will increase before then decaying back down to this base threshold. And how weight updates are calculated is by using the pseudo derivative. So this is that same hat function, which is centered around the threshold that I touched on earlier. It's multiplied by the incoming spike trace. So this is the spikes that come along that synapse are low pass filtered to create a running average of the inputs. They're multiplied by the pseudo derivative. In this term you see at the end, this is the adaptive threshold component of the eligibility. So if it was just standard leaky integrating fire neurons that are trained with EPROP, you don't include that. So it's just the pseudo derivative multiplied by the low pass filtered incoming spike trace. And then to calculate the weight updates, it's the eligibility that's calculated per time step. It's again low pass filtered. To create the eligibility trace, which is multiplied by this learning signal, which is the error multiplied by these feedback weights. So again, the feedback weight is individual for each neuron and for each output. And then you can do this over as many time steps if you want, and the learning rate will control how fast those weights will change. So to quickly touch on the neuromorphic that's used as well, we chose Spinnaker. Due to its programmable nature, it allowed EPROC to be ported to it. A typical board has 48 chips, and each chip has 18 ARM cores. The real-time computation meant that all experiments were done in real time, so it's a simulated robot interacting with a simulated environment. It also uses fixed point arithmetic. All the weights are 16-bit fixed point. So this presented a number of challenges trying to get this to work on Spinnaker. The main one is with EPROC, we wanted to retain the information of all the synaptic state. So generally, the synaptic state we kept in the SD-RAM because it has much more memory. But we needed to be able to access it at each time step to be able to calculate the eligibility, pseudo derivatives, which meant that it all had to be kept on the core. So have a much more restrictive memory size, which meant that there was only a certain number of synapses that could be kept in the core. So we ended up going for 8 neurons per core, which limited us to approximately 250 synapses per neuron, which was enough for the task that we needed. So the task that we actually the task that we did were first waveform matching. So this was a proof of concept in which we wanted to test the learning. So we presented it with a target waveform. We injected into the network a repeating Poisson spike source, which had the same repeating the same time period as the target waveform. The output neuron, we compared the membrane voltage with the target waveform to produce an error, and this error then is broadcast to the network, giving a learning signal to the neurons to be able to update those weights. The architecture is fairly straightforward. So we have these repeating Poisson spike train. You can see in the bottom left that the spikes have a temporal element to it as well. This was shown to help performance rather than just having a frozen input that was repeated. Having subpopulations firing independently at different time periods also seemed to help the network to have some temporal information to be able to better match the signal. The network itself only used leaky integrating fire neurons, so because there's no memory, there's no need for past state to influence future state, leaky integrating fire neurons were fine for this task. And the readout neuron population, this is the one that encapsulates the whole environment. So we have the neuron that's compared with the target. The target is also kept there to be compared against with the neuron. An error is calculated at each time step and then is broadcast back to the network in the payload of a packet. So in the learning process, you can see initially in the first presentation of the signal that there's a very poor match between the membrane voltage and the target waveform. But during this time, weights are accumulated until the start of the next trial, when the weights are passed into the network, the weight updates are passed into the network. You can see that even after the first update, there's a pretty good match. You can see that the membrane voltage now seems to have the same form as the target waveform. And then this continues until it has a pretty good agreement. At the bottom, there's the learning curve, which is fairly typical in its performance. You see at the start, it's pretty poor, and slowly or very fast increases, and then converges towards some performance. So the next task, this was the more complicated task. This is one that requires some memory of previous state. So this is where the adaptive thresholds really show their power. The task was a simulated mouse walking down the hallway. So as it walks down the hallway, it will receive a cue on the left or a cue on the right, continues to walk down the hallway. So again, you can see there's some temporal characteristic to this because it's not presented everything at once, presented each cue sequentially. And then after the final queue, there's a 1 second wait, and then it reaches the end of the hallway and has to decide whether to go left because there are more queues on the left, or to go right because there are more queues on the right. So this was encoded in the network as the inputs were one input for the left queue, one input for the right queue. When they were on, they fired 100 hertz pass-on rate. When they're off, they were 0. The prompt signal was given at the end of the trial, and this was to let the network know that you've reached the end of the hallway, which way is the correct decision. And there's also another input, which was just a constant 10 hertz pass-on input, which effectively acted as a bias for the network to sample from if it wanted. And the two outputs were for the left and the right decision, so I had to decide as it reached the end. So as mentioned before, receives the cues, there's a 1 second delay, and the prompt signal is given at the end. But because the prompt signal is only given at the end, this means that there's only error generated in that last 100 milliseconds, which means that there has to be something retained within the network, information retained within the network to be able to perform this task. And this is where the adaptive thresholds come in. So because there is this memory, the state that is kept, you can see this in the penultimate plot, where there's the eligibility, the adaptive component of the eligibility sustains until the end. So it can perform this update in the last 100 milliseconds, and just using that is able to solve this task. It's also worth noting that curriculum learning was used when doing this task, which meant that the difficulty was increased as it progressed. So we started off with 1 queue, then 3, then 5, then 7. So this was done in the original work as well, and it was shown to improve the performance and was quite important to solving the final difficulty of the task. So if we compare this to backpropagation through time, you can see that there's state saved within the leaky integrating files and the adaptive thresholds, specifically the adaptive threshold, that then allows EPROC to update its weights in the final 100 milliseconds. But with backpropagation through time, you generate the errors at the end, and then they have to be propagated back through the network, which means that you have to do another computation step backwards through time to be able to update those weights. Whereas EPROC can do all of this processing all online, and there's no interruption between interacting with the environment and learning. So the architecture is very similar to the one that was shown in the waveform task. So we have these pass-on inputs. The hidden population is now entirely adaptive thresholds. So we could have used leaky integrating fires, but because this is mainly a memory-based task, there was no benefit in adding them. The learning signal is generated by calculating the softmax between the left and the right outputs, depending on which was the correct one. And it's the readout neuron that really holds the environment of this task. So it's the one that determines, are we presenting a left queue or a right queue, and then keeps record of that to be able to know what the correct decision is at the end. So because this is all kept at the readout neurons, the pass-on rates need to be sent back to this variable pass-on spike train, the variable pass-on spike source. So this is in the same way as the learning signal kept in the packet of a spike and sent back at the appropriate times to update those rates. So this is a lovely GIF to grab your attention. You can see at the start, when this is just 1 queue, it takes a little while to kind of really pick up its pace. Performance holds pretty steady, can solve 3 tasks, fairly straightforward. So the vertical blue line is when it moves from one difficulty to the next, till it reaches 7 queues and struggles to perform. Until eventually reaching that and then resetting awkwardly fast. So that was sort of typical performance, where initially the start learning there is a significant amount of time at the start to learn these tasks, where it has to align these weights. I think this is where the curriculum learning is important, because if you jump straight to 7 queues, it can struggle to find this relationship between the inputs and the desired outputs, especially when spread out over time. Then moving up to the next difficulty, there's not a large difference, so it can perform that task relatively straightforward. And then in this example, it's the fifth queue that proved the most difficulty. So eventually it became too difficult for the current network to be able to perform, so there had to be further training. So in the previous task, this was when it was at 7 queues, and this one at 5 queues, until eventually it found a good balance and then was able to perform for 7 queues as well, relatively fast. So just to kind of wrap this up, as mentioned, there were a number of challenges presented by the neuromorphic hardware. So a lot of these were the memory restrictions. So sharing memory amongst cores was difficult, which influenced the way in which firing rate regularization could be done on Spinnaker. So with the TensorFlow implementation, you can average over the whole population because you have access to all this memory, and you can average over a number of batches as well, which allows you to estimate a good approximation of the firing rate. But on Spinnaker, because you're limited to a smaller subset of neurons per core, it's much harder to approximate those firing rates. So on the right, you can see two different scenarios, one in which we have a constant 10 hertz input over 8 neurons. And then you do two different ways that we attempted to approximate the firing rate, one in which we used an exponential decay. This generally worked all right, but it was quite noisy. And also you can use a window. So you just take the number of spikes you've received from the start and average it over the time length. So initially very noisy, huge spikes in rates until eventually it reaches a good approximation of performance. But then when you look at this with bursty firing, so this is something that we saw a lot in the temporal credit assignment task, because the inputs were quiescent, there'd be no inputs, and then eventually there'd be very high rates. It made it very challenging to be able to approximate rates within the network. So on the graph on the right, you can see that the exponential version does a very poor attempt to be able to match the target firing rate, where there's that red line, and there's actually only a fraction of time where it's good. And the windowed version eventually does reach the correct rate, but because of the bursting nature, it highly overestimates the firing rate of the network. So future directions this work could go in, moving to a multi-core model, so one in which the synapses and the neurons have their own core. This could allow more memory, more processing power to the individual parts, which could allow a better scale of the networks. Also, we'd like to do more with recurrent connections. So this wasn't explored, but it's one of the benefits of EPROP that allows you to compute with recurrent networks. But the main reason that we didn't or couldn't manage to get particularly good results from that, I think, comes down to the firing rate regularization. So because it's recurrent, it's quite easy to get self-excitation loops where just suddenly the whole network starts spiking loads, or the opposite, and just you get no activity because it's inhibiting itself too much. So there's a delicate balance that's particularly hard to do when you only can average over 8 neurons. It would also be good to be able to extend this to more complex tasks. So the EPROP algorithm was shown to be able to work for reinforcement learning tasks, going up to some really complex Atari games. So I think an extension of this work that could do something like Pong could have merit. Thank you for listening. Any questions?